Hi everyone, my name is Sebastian Paul and I'm a security research engineer at Bosch. I'm very pleased to present to you our work today in which we propose mixed certificate chains for the transition to post-quantum authentication in TLS 1.3. And this is joint work with Yulia Kuzovkova, Norman Lahr and Ruben Niederhagen. So looking at the field of quantum computing, we see that there have been many technological advances over the last few years. To give you just two examples, back in 2019, Google claimed to have reached quantum supremacy with their 53-qubit quantum processor. And last year, IBM presented its 127-qubit processor named Eagle, alongside a roadmap towards a million-qubit quantum computer. Nevertheless, the exact time frame until we see large-scale quantum computers is still up for debate. Experts estimate it could take another 10 to even 30 years before practical quantum computers will exist. But as you may know, this new powerful computing paradigms also comes with one major drawback. They can break all of today's public key cryptography, such as RSA and elliptic curve cryptography. And the reason for this is Shor's algorithm, which solves the integer factorization and discrete logarithm problem in polynomial time on a quantum computer. Therefore, at some point, protocols, applications, and network infrastructures need to be modified so that they integrate new cryptographic schemes that withstand attacks from quantum as well as classical computers. And this new type of cryptography is called post-quantum cryptography, or PQC in short. So far, 5 cryptographic families have been identified that are believed to resist attacks from quantum computers. That is the family of lattice-based, code-based, multivariate, and hash-based schemes, as well as the family of supersingular elliptic curve isogeny cryptography. And while I don't have time to go into the details of the individual families in this talk, they have quite different performance characteristics compared to the cryptography we currently use. And due to their novelty, trust in those schemes also varies quite a bit. As a result, the migration towards post-quantum cryptography will be a non-trivial task in many applications. So to initiate this transition, NIST started its standardization process for post-quantum cryptography in 2016. It is now in round 3 with 7 finalists and 8 alternate candidates remaining, and the winners should be announced any moment now. So at the latest, by the year 2024, we expect to have new PQC standards for key establishment as well as digital signatures. But this leaves us with one important question. How do we migrate efficiently to this new generation of cryptography? So up to now, existing migration strategies have mainly focused on protecting the confidentiality of communication against quantum attackers, which makes total sense since all data that is encrypting using conventional cryptography can be captured and decrypted once powerful quantum computers are available. To protect against this so-called store now, decrypt later attack, hybrid key exchange construction have already been proposed for several protocols. The idea in those hybrids is to combine conventional cryptography with post-quantum cryptography such that the resulting handshake is secure as long as one of the two algorithms remains unbroken. But what about authentication? While authentication cannot be broken retroactively, we still believe that the migration to post-quantum authentication needs to be completed before large-scale quantum computers exist. And that's because authentication is typically based on long-term public keys in form of certificates, as well as trusted third parties in form of certificate authorities. So we expect the migration of public key infrastructures to post-quantum cryptography and the replacement of sometimes hard-coded root certificates to be a very complex and also time-consuming process. And this challenge motivates our work. We want to propose and investigate a migration strategy towards post-quantum authentication for the network protocol TLS 1.3. And at the center of this strategy are what we call mixed certificate chains. And what that means is that we combine different signature algorithms within the same certificate chain. To illustrate this with classical cryptography, you can imagine you have a root certificate that is signed using RSA, and all other certificates of the chain would then use ECDSA, for example. In public key infrastructures, root certificates typically have quite a long validity period, and apart from maybe desktop environments, they're often quite difficult to replace. So for migration to post-quantum authentication, we require algorithms that are already mature enough for real-world deployment. And in our paper, we argue that hash-based signature schemes like Sphinx Plus and XMSS fulfill this requirement. Mostly because they only rely on hash functions for their construction, and their security argument requires only on minimal assumptions. Besides that, stateful schemes such as XMSS are already specified in an IETF RFC and are also recommended by NIST for certain use cases. However, due to their long signing times and large signatures, it's challenging to only use hash-based schemes in a single certificate chain. Therefore, we need faster and more balanced schemes at the intermediate and end entity certificates. And for this, we see lattice-based signature schemes as potential candidates. They've seen quite a lot of attention as part of the NIST standardization process and offer fast signing and verification times. Nevertheless, their security is not fully understood yet, so it would be too early to already deploy them in real-world systems, especially within root certificates. Therefore, in our migration strategy, we start with hash-based schemes at the root level of a PKI and combine them with conventional elliptic curve cryptography first, which we consider as an intermediate migration step. Then, once lattice-based schemes reach the same level of maturity as hash-based schemes, we replace elliptic curve cryptography with lattice-based schemes to have a certificate chain that offers full post-quantum authentication, which would then be our final migration step. I should also add that with this strategy, we do not hope to see faster connection times in TLS compared to the conventional case, but rather to simplify the transition to post-quantum cryptography by keeping the overhead due to the extra signature schemes as low as possible. Since we also think this kind of migration will happen alongside the migration to post-quantum confidentiality, we use Kyber for post-quantum key exchange in our experiments. So first, we had to integrate post-quantum signatures and post-quantum key exchange into the TLS 1.3 handshake. And as in previous works, the idea here was to replace all conventional public key cryptography with post-quantum key establishment and signature schemes. This way, we keep the original handshake structure in place with all its security guarantees. And we only need to change the content of the relevant handshake messages and operations on the client and server side. And regarding this implementation, we worked with wolfSSL, and our code is also publicly available on GitHub. The figure here shows the resulting handshakes. So for our migration strategy, we work with certificate chains of length 3, and we consider mutual authentication in our experiments. So after the integration of post-quantum authentication into TLS 1.3, we get 8 operations that are related to post-quantum signature schemes, which are the orange boxes you can see in the figure. And finally, we also have 3 operations that are related to post-quantum key establishment, which are shown in yellow. So next, let's have a look at the evaluated scheme combinations. We selected the stateful hash-based scheme XMSS and 2 variants of the Sphinx Plus signature scheme, a speed-optimized instantiation, which promises faster signing times, and a size-optimized one, which offers smaller signatures and faster verification. And regarding the lattice-based schemes, we selected Dilithium and Falcon, which are both finalists in this standardization process. And for the conventional cryptography, we used ECDSA. From this set of algorithms, we then derived 4 evaluation groups. The control group contains 6 regular certificate chains. And we compare our mixed certificate chain against the conventional certificate chain based on ECDSA. The 3 groups that represent our 2-step migration strategy always contain a hash-based scheme at the root certificate level. And we combine that with ECDSA at the other levels as part of the intermediate migration step first, and as part of the final migration step, we evaluate the hash-based scheme with the 2 lattice-based schemes. Therefore, we get 3 scheme combinations with XMSS being used at the root level, 3 scheme combinations with the speed-optimized variant of Sphinx Plus, and 3 more scheme combinations with the size-optimized variant of Sphinx Plus being used at the root certificate level. Regarding our hardware setup, we work with 2 client devices, a standard notebook and a Raspberry Pi 3. In this setup, the notebook represents typical desktop computing environments, while the Raspberry Pi represents an embedded client in a more resource-constrained IoT environment. The servers, on the other hand, are set up as virtual machines at 3 different locations with increasing distances to our local clients, as you can tell from the round trip times in this figure. So the closest one is based in West Europe, one is located on the east coast of the United States, and another one in East Australia. To demonstrate the feasibility of our approach, we wanted to obtain as many measurements as possible. To do so, we looked at time-related measurements as well as cost-related measurements. Regarding our time-related measurements, they consist of TLS connection establishment times, where we mainly focus on time to first byte, as well as performance benchmarks of the individual cryptographic primitives on all evaluated platforms. In our cost-related measurements, on the other hand, we report communication size, library code size, and peak memory usage of our client and server program. However, I won't have time to go through all the results in this talk, so please have a look at our paper for the complete picture. So first, let's have a look at the connection establishment times. For the 2 client devices, we measured 1,000 TLS handshakes for each scheme combination and each remote server. In case the 2 clients connect to the server based in West Europe, you can see from the figure that the increase in median time to first byte across all evaluated mixed certificate chains remains feasible. Compared to the ECC-based control handshake, this increase amounts to 12.4% in case of the notebook and 14.4% in case of the embedded client. Now, when we look at the intermediate migration step, we see that a combination of XMSS with ECDSA is feasible, as well as the combination of the size-optimized Sphinx Plus variant with ECDSA. And regarding the final migration step, the combination of XMSS and dilithium gives very promising results. It had the fastest time to first byte, and it even slightly outperformed the elliptic curve-based control combination on the embedded client. So moving on to the cost-related measurements, I will focus on peak memory usage here. For this, we looked at the heap and stack usage of our client programs using Valgrand's Massive tool. Since heap usage is mainly affected by dynamic memory allocations that are related to the message buffers, it's not very surprising that we observe an increase of heap usage across all evaluated combinations. Peak stack usage, on the other hand, depends more on the implementation of the actual cryptographic algorithm. But since heap and stack both reside on RAM, it's very important to achieve a low memory consumption for both, since this is typically a scarce resource, especially on embedded platforms. So regarding the intermediate migration step, the combination of XMSS and ECDSA again leads to the smallest increase in peak memory usage, which was around 5%. And in case of the final migration step, the combination of XMSS and Falcon leads to the lowest increase with about 30%. Dilithium, on the other hand, requires quite a bit more stack and heap memory than Falcon, as you can see in this table. So to conclude my talk, we presented a 2-step migration strategy towards post-quantum authentication based on the concept of mixed certificate chains. Besides that, we showed that this approach is also feasible in TLS 1.3. Regarding our intermediate migration step, a combination of XMSS and ECDSA showed the fastest connection establishment times, lowest overriding communication size, and lowest memory usage. We also believe that this is a valid strategy since hash-based schemes offer conservative security against current as well as quantum attacks. Therefore, they are a perfect fit for the high security requirements of root certificate authorities already today. Besides that, since they are only used at the root level, many of the drawbacks are mitigated that way, such as their slow signing performance and large signatures. So finally, regarding our final migration step, a combination of XMSS and dilithium showed feasible connection establishment times on our 2 client platforms. However, its impact on RAM was more significant than we've seen in other combinations, such as XMSS combined with Falcon, which was mostly due to the larger key and signature sizes of dilithium and its higher stack usage. So depending on what algorithm will be standardized by NIST, memory optimized implementations may be required as part of future work. So Thank you very much for your attention.